Before we start, how many of you are familiar with Scala? Please raise your hand. Have used it? How many of you are familiar with, have used or familiar with cascading, the underline? Okay, some more. So since some of you still are not familiar with Scala, we'll just start with the infamous word count job, because you cannot really present a big data framework without counting some words with it. Otherwise, how would people know it actually supports big data, right? So here's the text, and scalding, as you can infer from the name, is written in Scala. And just we'll go kind of line by line. So we have this word count job that gets arguments, and extend job, which is the scalding job type. Basically, this whole boilerplate of what you get with vanilla MapReduce job with setting a bunch of settings is just this one line of this is my class and extends jobs, and the job class does everything for you. The first line is, so scalding has multiple APIs. One of them is the fields API, which is more resembling the cascading API, which is kind of you can think about it as this giant tuple that has multiple elements in it with different types. If you are familiar with pig, so pig operates also in a very similar fashion. The other one is the typed API, when we actually work very similar to the Scala collection API, or if you are not familiar with Scala, think about this Java collections, where we actually have types and we can do operation on these types, and the compiler kind of guarantees the type safety, and it's actually very nice. So the first line is just read from the input, kind of just a bunch of strings. The second line is what call it flat map operations. Basically take every line and tokenize the line. Tokenize, you can see at the bottom, a tokenize is just a Scala. Again, if you come from pig, we might call it a user-defined function. It's not a part of the scalding functionality. It's something we define as an auxiliary method for us to use. And the flat map means is basically transform it to this array and also flatten it afterwards. So the type we get after performing this tokenization, instead of just so sorry, I forgot to mention that type TSV returns something that is called a typed pipe. It's like a collection of lots of records in it, and we can perform operation on all of these records. Like map is transforming from type A to type B. Flat map is transforming from type A to, again, type B, but the B first returns as some sort of sequence. In this case, tokenized returns, as you can see, array. The next line is group by, and identity is basically means group by whatever it is you have. Identity is like a function that takes X and return X, the mathematical identity function. So it's also, in Scala you can use it, but basically what I'm trying to say here is group by whatever string you got from the previous line. And then for each of these groups, so whatever comes after the group is just size, give me the size. So what you can see here that I will finally get a string and a long attached to it, which is the long is just how many times I saw each string. So other way to think about the group by operation, at least how it implement the Scala collection, think about that we get kind of this dictionary that maps between a string once we do a group by, and then a list of all the elements that are mapped to that certain strings, and then we just perform the size operation on that string, and we get every word with the length associated with it. And this just goes to show that what's kind of nice about using frameworks, again, and pretty much everything I will say today, I'm going to say it again, is true for Crunch, Cascading, Scrunch, Scooby, Scala, all this kind of frameworks where you actually use it's not a domain-specific language, but it's actually either Java or Scala, a language where we write our jobs in, that we can use the native language, the language we operate to write our kind of data processing logic, the group bys, the joins, and the maps and the filters, is the same language we wrote our auxiliary function, in this case, tokenize. So if you look, tokenize is just a function in Scala that gets a string, performs this lowercase replacement, and then split by any amount of spaces and return an array of strings. And we can call these functions for pretty much anywhere. And it's kind of nice because if you compare it to a framework, for example, like Pig, where you write your data transformation in a domain-specific language, but if you want to use a user-defined function, then you have to actually implement it in another language. This language has to be either, again, Python, Java, or whatever. I think they have support multiple language, but it's kind of create this inconsistent code where you have some part of the code in one language and some part of the code in another language. So that is how you perform word count in Scala. And again, if you take this code and you can find it on the Scalding wiki, it's the code you will find is not the types API, it's the fields API, but you can also in the wiki find information about how to go from the fields API to the types API and vice versa. Is you just run it and you can basically just run it on your cluster and it will work. That is the entire code. There is no a lot of boilerplate that I've hidden here. This code will just run. Yeah, but here we go to our second meme. And for everyone that's seen the movie Office Space should be familiar with it. But basically, the meme is called "That'd Be Great." And here I say, well, so we're reading this code, but it's just one kind of, it's not how we write any other type of code. We don't just write all of our logic in a main function when we're not writing data stuff. But for some reason, people do accept it when they do data processing. They write just their entire code, the entire logic in just one file and keep this code that way. So let's try to write the same code in kind of more reusable way. And this meme, "That'd be great," is again something, something, something. And if you can, if we could just go ahead and do something, that'd be great. Here are two other examples. The Google Fiber is totally true. So yeah. OK, so we can just declare in Scala the word object basically means a singleton, or you can think about some kind of version like a static class with methods that are not instance method, but a method of the object. So we just define here the common object. We still have our tokenized function we need, and let's kind of do the count words function. It's exactly the same code, but it just gets word. And again, here we have the assumption that the words are already tokenized, and we perform the same group by in size. But now what's nice about it, that we suddenly have the concept of a function that we can reuse, and someone else can call that function as well if they need to count words, right? And we say, so again, the Scala syntax is, so there, count words is the name. It gets words from type pipe of string. So this is the Java generics, the square brackets. And it returns, like we saw, a type pipe, but instead of just a string, each string will be associated with a long that stands for the count. So again, all we did here is instead of taking our code inside a kind of big job definition, we created a function that we can use. And even though it may sound trivial, I really want to iterate the point how functions are important. Because for a lot of us that use pretty much any language today, we're kind of are used to thinking in function. We break our functionality into function. But for some reason, when people move to like this whole big data, data science, call it however you like, suddenly, yeah, we don't need to. All the code became ad hoc stuff. Yeah, so we have this task, we have this file, and we need to transform it to another file. Let's just write one piece of code that does the transformation without kind of thinking about, well, someone might use it as well, and he might have a slightly different input or might have a slightly different output. And that brings me to the third. This is the Morpheus meme, which it doesn't actually say it in the Matrix movie. I actually checked, and he never says, what if I told you, but you don't see, but it's a picture of Morpheus from the movie Matrix. And the meme goes, what if I told you? And here, well, we can count more than words. So every time we see this MapReduce framework, we always see the the word count. But we can count more than just words. Let's, instead of count words, now try to do the function CountAnything. And again, we're going back to Scala and the nice things about it, a type-safe system. And we're saying, OK, well, let's declare a kind of generic function that's called CountAnything. It's of type T, and it gets elements of type T. And it just returns a type pipe of T and long. And again, the logic is exactly the same logic. We are not doing anything that is string specific, so we don't need to actually kind of bound ourselves to counting words, because again, if we don't perform any string manipulation in this specific function, then we actually don't need to use it. And again, it goes, now so if before we reach about the 70s when we actually started to use functions, now we're kind of in the 90s when we started to use generics, right? And maybe I get the computer science wrong, and probably there's a lot of language experts that will correct me to say that generics were probably existing before, and it might be true. But again, it's still very basic stuff that you won't find in most data flows, that people just don't think about, OK, well, if my stuff works on strings, let's see if it can work on other types as well. So this is, T. And the question is, will it work? So can we just count anything of any type? Anyone has a suggestion? Can we just count in MapReduce anything of any type? So it's kind of a tricky question, and well, it's not tricky. The answer is no, but let me just explain why. Is because the way MapReduce actually works. So we call it MapReduce, but we forget there are actually 2 more stages in every Hadoop MapReduce flow, which is the shuffle that actually explicitly stated here. And in the shuffle is basically what it says, that every key that we group by needs to have the sort of equivalent of a hash code, right? We need to know how to take any arbitrary object and how to send it to a reducer. And it's not necessarily trivial, or we can just infer it from any type of object. And so again, here the T can stand for anything. It doesn't have to be int, string, or long. It doesn't have to be only primitive types. We can have records of object person, and we can group by this and we can count people. We can have classes that can be any type. But this type has to have this basically kind of hash code thingy in order for us to know where to send it. The other thing that this type must have is because, again, if you remember how at least the job tracker of Hadoop looks like, so we have the shuffle that also called the copy stage when we look at the job tracker. And after the copy stage, it comes the sort stage. So actually, the Hadoop MapReduce framework guarantees that also within the reducer, all the keys will be sorted within any single reducer, and that is why we also need to have some way to sort the keys. Think about it, we need some ordering. So the way to actually change this code to work, and again, it's kind of Scala specific stuff, but what you can see, it's kind of pretty nice that we can say, okay, well, it's not just any t, it's t that has an implicit ordering. It's not very important for the scope of this talk to understand how exactly it works, but we just kind of limit, we do a context bounds on the types that we support with CountAnything, and we say that we can count anything as long as it has ordering associated with it. Okay, so this meme is sudden clarity Clarence. It's basically a guy that suddenly realizes something. And in my example is, we call it word count, and but basically it's just a histogram of words. We have a term for this thing that usually refer of word count. So let's look at now. We can actually define a class histogram, and now we come to our next kind of evolution in MapReduce code, right? It's class. So again, the case in Scala means, for those of you who don't know, it's just a kind of a short version of a class that you get the kind of nice constructors. So the constructor here is this pipe, or we don't need actually to define constructors and getters and setters and stuff like that. And we also get the hash code function, and the equals function already goes, it's like with one magical word case, we get kind of additional functionality that usually just boilerplate in the regular code. But that's not just important, but we can say, okay, everything that has ordering with it, we can count it, and let's just create a histogram object that gets a pipe, and then we can define functions on this object that we called histogram. So we have something that we counted, and we can do more than just return the counts. We can do the size, which is just the sum of all the values, which is actually the way the sum works is, well, almost magic. It's but I think we'll see an example later about how this magic actually works, so let's just leave it for now. But basically, it sums all the operation and returns us a value pipe of wrong. What I actually forgot now, I noticed here, I don't need to sum all the elements. I only need actually to take the values. So I forgot one thing there, but never mind. And we can also call other function. We can, if we have a histogram, we can compute the standard deviation, the cumulative distributive function, the median, the Q1, the Q3, and we can actually use the other function to define other things like the inner quadrilateral range as Q3 minus Q1. Again, that is just a code of showing that we can do this stuff. We not necessarily should do stuff because every operation here will kind of be equivalent of a MapReduce jobs, and there are other better ways to do so. But the slide here is just to show that suddenly we can have abstractions over abstraction, and that is how we write usually pretty much any other code we write in our day-to-day. This is how we do it, but suddenly again, when a lot of people turn into this data flows, they tend to forget about these kind of abstraction and just solve things in a very ad hoc way, which is missing a lot of the point that a lot of the best practices that the last 40 years of software engineering brought us. Yeah, so size function returns a value pop of long. It does sum, but what I needed to do here is between the pipe and the sum, I actually needed to get only the, like I said, the second element of the tuple and then perform a sum on it and to get back a value pipe. So why is it value pipe is kind of a thing in Scalding, which is basically, it means a tight pipe of size 1. Actually, it can be not just size 1, but for this argument, is because we usually sum returns as a single number, then we have kind of a special class to indicate that the function size will return a pipe with just a single element in it. OK, and now, since also we are actually using a real language, and it's not just a DSL to compute data stuff, we can use other nice things this language has to offer. And in this case, is Scala. And Scala has this pimp my class pattern. And again, without going to too many details, is the pimp my class pattern looks this way. So we can define an implicit function, which is what the implicit def means, and we call it toHistogram. So it gets a tight pipe and just converts it to a histogram using the constructor of the histogram we saw before. And the reason why you don't see the word new before the histogram, like in Java, is because we define our class as a case class. And another one of the nice things that it has to offer is we don't need the boilerplate of the new keyword. We just can return the histogram of pipe and understand that I need to call the constructor of histogram with my pipe. So why is this kind of implicit definition good for? Is because the Scala compiler works in this way that we can now call functions from the functions of the object histogram on things that are not type histogram. They are of type pipe of string and long. And we will actually, the compiler will go and look whether it has these implicits in scope. So basically it asks himself, do I know how to convert a type pipe into a histogram? And if so, then it just calls this conversion. And now we can call the size method we defined before on histogram on the word count. So we don't actually need to first transform this word count into a histogram. We just call size on it. And again, just to be clear, the point of this entire thing is not to show that Scala has implicit conversion, but to show that once we're using a real language, is actually we can use some of the things that this language has to offer. In the case of Scala, it's implicit conversions, but there are more. Yeah, so. OK, so this is condescending Wonka. So basically, OK, so I've been talking a lot about counting stuff, but it's not actually data science, right? It's just counting words. At some point we need to go beyond. There are like a bunch of tutorials, and well, at least mine is like half of the time went on, yeah, it's pretty cool. We can count stuff. I'm a data scientist. So please tell me more about this data science of yours. And again, just, for people who are condescending and witty on the internet, this translates very well. And these are just another examples, also a pretty cute meme. So the truth about at least data science and the MapReduce concept, that most of the interesting work is not happening in the mappers. The mappers, in most cases, just take data of type A, transform it to type B, maybe filtering. In some cases, they, some do kind of very specific joins. But the most interesting work is actually happens, once all the data funnels down to the main guys who are the reducers, and they do the actually heavy lifting, and this is where all the data science magic or whatever it is happens. And here is one example of I chose to portray here oh, you can't really see it, but basically it's a basketball player, it's the Miami Heat. And you can see that LeBron James is here in the blue. And we have the mappers whose their job is like just to take the ball, give it to the reducer, and the reducer needs to finish the job, and he's the one who's doing the fancy stuff. The other ones are just there to handle the ball. Okay, so let's look. So we saw a sum, but we can also do other stuff on histogram. And one of them is mode. So what is mode, for those of you who don't remember, is basically find the most common element inside our histogram. So the statistical mode of a distribution is the most common element in that distribution. So again, we define mode that returns a value pipe of the tuple of t and long, which the tuple is basically the most common element and the count associated with that most common element. And the first thing, let's just define a max function between two of these tuples. And it's pretty straightforward. In Scala, if the second element, which is the count, left second element is larger than the right second element, return left, otherwise return right. Just we define a function because it's not exactly clear if we have two tuples and we want to get the larger one of them, how exactly we can achieve that, so we just define it. And now we are calling the function aggregate of pipe. So function aggregate is like, I think, where 90% of like Scalding's magic happens, but basically it's just a wrapper for the MapReduce map system. So what aggregate does is takes data, and here so let's first mention just the from reduce. It takes some function that can takes two elements of the same type as our pipe, and it basically reduces it in parallel way until we remain with only a single element. And just kind of one thing that we should notice, again, it won't work on every function. The functions have to be, in order for it to work, the function have to be associative. And for those of you who don't remember what associative means, it means that if we have A, B, and C, then doing the computation on A and B first, and then having the result with doing it with the result in C is the same way as doing it with B and C first. Like a sum is an associative operation, and a product is also an associative operation. It doesn't matter which order we do it, and that's extremely nice, this property for parallel processing, because basically in parallel processing we don't know in which order the computation will happen, but if we guarantee that our computation is associative, then we know we will get the right answer at the end. And here basically we're saying, take all my data for every two elements, just perform the function I just described before. And the function here, I haven't explicitly mentioned it, but it needs to be a function that gets two elements of some type and return an element of the same type, because otherwise, it will just all break down. And we call this from reduce, and every time, just for every two, it picks the max, and eventually we will have the max in like this very nice distributed parallel fashion. And basically, this is how we compute the mode. Again, take all the elements, max them together, and return, the one, the person left or the tuple left standing. So what we can do is we can actually generalize mode, right? Mode is return the top one element. Can we generalize the same pattern to return more than one element, more than one top element. So there is a very inefficient way to do it. And it's basically, so pipe group all means send all of my data to a single reducer. And sort it by the second element. Reverse means sort it in the reverse order. And then take the top k and just return the values it means because, well, it doesn't really matter. So obviously the problem here is that in order to get only the top few elements, we are sending all of our data to a single reducer, which is a single machine, is like some memory-bound processor, and we're sorting all of that data and then just taking the top few elements, which is, again, as you all can probably understand, it's extremely inefficient. So there must be a better way. And again, we have here aggregate to the rescue. So one other way to do it is actually to run through our entire data, and it's very similar to the way we did it with one element. So if you kind of think about how we do it in an imperative paradigm, when we want to find the one maximum or minimum element, what we do is we set, in case of maximum, then we set a new an element to equals to, well, if it's int, like to the minus n or null or whatever it is, or the first element, and then iterate and always compare, and as long as it's in the, if it's larger than the element we have so far, then we just swap them and get our result. But we can generalize it, and also in an efficient way with a priority queue. So instead of just holding one element in memory, we hold a priority queue. And every time we try to we insert, priority queue with a limited size. So here the priority queue tool is aggregator k. So k is the size the size of how many top elements we want to get. So we run through our entire data with a priority queue, and basically for each element, we say, OK, well, whether this element should go into the priority queue. If so, then we remove the other element. If not, then we just discard that element and continue to go. So if you remember the property, the associative property I mentioned about the max function. So max is definitely associative. It doesn't matter in which order we compute max. It will always, we will get the maximum element at the end. So for example, and not associative things is, for example, is median, right? In median, it might make a difference how we, in which order we perform our computations. So this associative property is also true about priority queues, because we can take two priority queues and actually merge them into a new priority queues. If, let's say, our priority queue have 5 elements, so it's pretty simple. If we have two priority queues and both of them have like a single element in them, then the justice will combine them to a single element of a single priority queue that has 2 elements. If we have, let's say, each one of them has 5 elements, which is the maximum that it will have, then we'll basically create a new priority queue that has the 5 largest elements in it. And it also doesn't matter in which order we're doing it. So we, again, using the aggregate method, we get this very nice functionality of we can perform this operation in a completely distributed manner, and we're guaranteed to get the right answer at the end. So if you see just the syntax of priority queue, so it gets the first parameter is how many elements, and the second parameter is basically the parameter of the priority queue. What is the ordering? How do we define which element is the largest? And here I'm basically the minus second element means the second elements in reverse ordering. Since we're using longs here, then the minus operation is defined, so we can use it. The reason why I have a flat map at the end is because priority queue actually returns a single list, and a list. But if we want to get several elements and not just a single list, and I see I have another error here in the slide, I apologize for that. I was kind of making them in too late of an hour, but basically what we will get is a pipe. Instead of value pipe, we'll get a type pipe with multiple elements, depends on k. But again, the point of the slide is we're using the same aggregate method with an associative reduction in order to get something kind of neat. And this is, well, 2 is not a pattern, but here we can obviously see that we're kind of seeing here a pattern that we might have followed. So we see that we have this pattern of pipe.aggregate and then some aggregator, and whatever this aggregator does, we get something at the end in a completely distributed manner. And yeah, so the aggregator, that at least what we show, there's multiple ways to define this aggregator, but the easiest way is to use the from_reduce function that, again, gets 2 elements of type T and somehow reduces them to a single element of type T. So the arrow here means basically reduce is a function from a tuple of size 2 of 2 elements of T, and it returns a single element of T. So you're telling me I can define all my reducers with one simple function? So the answer is no. We cannot define all the operation we can think of within a single reduce function. That, well, scaling provides a lot of magic, but just not as much. But we still can do a lot. And here is the type of aggregator that actually are both has this very nice associative and actually it's commutative properties that are not trivial, but they can be entirely used in this kind of fashion. And Oscar here, who is one of the authors of scaling, who is sitting here, he claims that pretty much anything we do can be described in this fashion, as it's basically an associative operation. So you can try him after the talk and just think about any algorithm and try to see if you can solve it with this one simple reduce function. So some of them is count, some the minimum, the maximum is, like we say, Boolean operation, the AND, the ORs, concatenation. So for example, actually concatenation is not a very good example, but set and hash map operations is also, it's kind of very similar to Boolean operations. Like, for example, a union or an intersection are also, it doesn't matter in which order we perform it. Same with functions composition. The specific type of function, it doesn't matter if we apply, F and G or G first and F and stuff like that. Moments. So the 4 moments, which are the average, the standard, the variance, the skewness, the kurtosis, are all associative operation priority keys we just see. Bloom filters are also, we can just take 2 Bloom filters and join them into a single Bloom filter, and it doesn't matter in which order we do it, so we can do it in a completely parallel way. Min hash is this very cool technique, kind of reducing a set to a single or several hash functions. And one of its uses is to do LSH with locality-sensitive hashing. So basically, we can reduce the dimensionality of stuff. Hyperlog, which is commonly used to estimate the cardinality of a large data set. So for example, if you want to know in a kind of probabilistic manner how many unique elements you have in a data set. So for example, you have like billions of rows, but you're only interested to find the the unique IDs, and you want to do it in a kind of very fast and efficient, but but you don't have to get the the exact number of unique elements, but you can you can do it with 1% error, or you can actually define whatever percent you want. So there is a trade-off between memory and accuracy. Hyperlog is one of these operations that, again, is very simple. It's just a reduce function that is already defined, I forgot to mention, in the libraries that's called algebird, which is algebra and a bird, because everything in Twitter has to be named after a bird, even math. So algebird has already, you don't need to do it. All of them are already defined for you. Count, min, sketch is, again, a probabilistic data structure to estimate histograms. So if you don't need your exact histograms because they take too much space, but you want some data structure that is confined in a certain memory space, which allow you for a pretty accurate estimation, but not exact, and you can live with it, then count, min, sketch is one of these tools. And again, it's just a reduction. And also stochastic gradient descent is also one of these operations that you can perform in a distributed manner. And these functions, while they're extremely useful in the batch Hadoop world, they're also they're much more powerful than just performing MapReduce with them. If you have streaming systems and you want to calculate any one of these in on a streaming data, then having this associative and commutative property on the operation you're performing is also very powerful, and you can also use it on streaming data and not just batch mode. And I invite you to, if you're interested in the streaming, to look for one of the Oscar's talk about Hummingbird, which is this framework this framework to do both streaming and MapReduce in one code base. So yes, it's so this property, when you have a function that is associative and commutative and takes, is called a monoid. To be more exact, it's semi-group, but again, it doesn't matter. Monoid is just a name, and they're everywhere. They're literally the amount of times that I was writing this operation that I thought is complicated, but then I realized that I actually can implement it as this one simple reduce function, is actually mind-blowing, and also why the point of this talk was about opening your mind to abstract concept of functions. So if you think about it, it's and sorry if I sound an enterprise guy for 1 second, think about it as a design pattern for data. But it's far, far, far simpler than a design pattern. It's like you saw the entire pattern. It's just a function that takes 2 elements and return 1 element of the same type. That's all, and probably this pattern, at least for data work, will serve you so much better than any of the abstract factory lens method, patterns that you read in this, design patterns bestsellers. So monoids, they're everywhere. And this is a Buzz Lightyear basically it goes X everywhere, and X can be, well, anything. So we're good on time, and just final thoughts. First, memes are awesome. I don't know if I managed to convince you, but if I did, just go to Reddit and then send me hate mails for just the ridiculous amount of time you spent on just going through this crap. And I don't know, I'm just addicted. It's like I just look at the links, and it has 100 links, and they all purple because I clicked on all of them. And I don't know, it's just, it's a picture with words on it. And then they have like pictures of cats, sometimes dogs. There are more cats people than dogs. And not just rated, there are like 9gag and other websites, but they call themselves the front page of the internet, which I think is like an awesome way to describe your website, is the front page of the internet, and it actually like tells you in one sentence. So if any of you like, a startup person that now just like thinking about how to kind of brand his company, Reddit is definitely one good example about how to do it. So my second point, besides memes, but obviously the second and third is not as important. The second is ease of use is one of the criteria. So frameworks like Pig and Hive, they're very easy to use for very basic stuff. And disclaimer, even though I don't like Pig, I still use it for ad hoc stuff. So if I need like to find one single record that I know what is the key, and I just need to find it very fast on our clusters, I don't spin up a scalding job in order to do it. I just go to the shell and say, find me this record. But actually now, scalding finally has a REPL, right? So yeah, don't use Pig. Just you don't need it. So scalding finally has a REPL as well. But if you want to do a little bit more science-y stuff, and again, the stuff I showed is, again, I don't know if I actually call it science, data science, it's, just a terminology, but a little bit more complicated stuff than, counting or selecting elements. You need some frameworks that will help you to do so, and, you can do so much worse than scalding. And kind of the more larger point I was trying to make, that the modular, reusable, and eventually simpler, and I call it eventually simpler because there is some learning curve to Scala for, to the functional concepts I talk about, to this monoid thing, which is just, scratching the surface of category theory, and this is like a bunch of other stuff that, makes us better at what we are, but we don't have to know everything, but at least just kind of realizing that some of the stuff we do have a pattern, and this pattern has a name, and and there's other things that fall into that pattern will make us so much better professionals in what we do. And I'm not saying that as one of these better professionals. I'm just saying it as a guy who suddenly realized, just my eyes were open that, there a lot of the stuff I do is, is already solved problems, and I don't need to solve them again. And they can be as simple as monoids, which is basically just an operation that takes 2 elements and returns 1 element. That's all. That's all. Thank you.